Okay, so we're going to start today, first couple of days of our new unit, and we're looking at rational expressions. And we're going to start with a real life example. The reason is so often we do rational expressions and rational equations, it's hard to get real life stuff. So we're going to start with the real life stuff, and then we'll move to some more abstract stuff later, but at least it gives us an idea of where this is coming from. So if you haven't already, I want 5 minutes. Just quickly read the worksheet that you have in the scenario that we're talking about, and then graph the first few points from this table onto this graph with the number of workers along the bottom here. So number of workers goes here. And the hours goes over here. Okay? So if you need a couple of minutes to do that, pause the video now, and then we'll continue on. Okay, so we're back, and we're going to start answering some of the questions, and we're going to go through this all together. Okay, so for starters, what happens to the cleanup time when the number of workers is doubled, tripled, or quadrupled, and see if we can identify a pattern. So let's just have these two upside each other, and then we'll talk about it. So you've had a chance to read the scenario, and I think right at the beginning the pattern makes sense. So the idea makes a lot of sense. We say it takes one worker 18 hours to clean up at the fast food restaurant. And then if you get a buddy, then obviously that work is cut in half. So the first thing we'll notice is if the number of workers doubled, then it would take half as long. Again, we're making lots of assumptions that the two workers are working at the same time and the same pace, and you know they're doing everything exactly the same. It just makes it double, or there's two of them, and so it's half of the time. Again, looking at what happens when you triple it, and we see that when it's tripled, we get a third of the time, and quadrupled is a quarter of the time. The overall conclusion is, of course, more people is going to result in less time. So this is very different than relationship than maybe the ones we started off in grade 9 and 10. Like in grade 9, when we had more people, it meant you had more costs, for example. You know, like if it was $5 per meal, the more people, you had more cost. Well, this is inverse of that. The more people means less time. So number 2, if you find the product of W and H for each order pair, what do you notice? Well, of course, if you take the product, 1 times 18, is 18. 2 times 9 is 18. 3 times 6 is 18. So obviously W times H equals 18. And why is that? Well, it's always still going to take 18 hours to clean. Or sorry, there's still 18 hours of work that has to be done. So although it may take longer with more, or sorry, less time with more people, there's still 18 hours of work. So regardless of the number of workers you have, it's going to be multiplied by the number of hours. You're still going to get 18. So now you were asked to sketch it. So let's just look ahead and see what the sketch looks like. So you have these points, number of workers along the bottom, cleanup time there. And it asks in this number 3 to extrapolate this. So we're going to go on and continue the pattern a little bit. So we stopped at 6, and 6 it took 3 hours. So then if we went to the next one, 8 people, it would be 2.25 hours. Be about here. Sorry, that was 7. That's for 8 people. 2.25. 10 people, it would take 1.8. And I'm getting this by taking the 18 hours and dividing it by the 10 people, so that's 1.8. 18 hours divided by 11 people is 1.67. So, you know, I've got a couple of points here. And I think it's pretty safe to say that we all recognize this pattern as a nice smooth curve that goes like this. in number 3, it says, what do you notice about the changes in the shape of the graph for very, very small and very, very large number of workers? Well, I think it makes sense that as W gets larger and larger, what does the graph do? Well, as the number of workers gets bigger and bigger, this graph gets closer and closer to 0. Very small. Which makes sense. And vice versa, as W is smaller, so less people you have, then H is very large. Like only one person, it's going to take 18 hours to clean. Use at least 2 pieces of data of evidence. So we're looking at number 4 now. Use at least 2 pieces of evidence establishing this relationship is linear or nonlinear. Well, I mean, the graph clearly shows that it's nonlinear, and also the first differences are not the same, so it's nonlinear. We do the first differences here. We got 18 to 9, it goes down 9, so down 9, and then from 9 to 6, it goes down 3. To this one, down 1.5. It's not the same, and so it's nonlinear. Number 5, as you increase the number of workers to very large numbers, such as 1,000, what will the cleanup time approach but never equal? So if we continued the graph on and we went all the way down to 1,000 workers, which again is a little unrealistic, but it would still come really, really close to 0. But would it touch 0? Well, no, because there's still work that has to be done. And if you had 1,000 people there and you had to clean the floor and everyone was in charge of one little piece of the floor, sure, it'd get done really, really quickly. But as soon as you say go, it still actually has to happen. So there's still at least some time. It's going to be a very small amount of time, but at least some time still has to pass. So it approaches 0, but it never equals 0. So we're going to say it's essentially 0. It approaches 0. And this is a calculus idea that we're going to spend more time on next semester talking about. But essentially, it gets close to 0, but not actually 0. So we know the graph comes and gets really, really close to it. And vice versa, if we consider the other case. So we know that one worker here took 18 hours. Well, what if you had half a worker? Now, again, that's not really realistic. But let's say it's the one person working at half speed. So it's like half a worker. Well, then the time is going to go up to 36 hours. It's going to take twice as long, right? And again, if you get that even smaller, like a 0.1 worker, 0.1 worker would be like a worker working a tenth of their pace. It's going to take a really, really long time. And if you get really, really slow person, that amount of work is going to be infinitely huge. So it's going to approach, it would move towards infinity, right? A positive infinity. So if you had the slowest worker possible, it would take virtually infinity amount of time to complete. So the fact that the graph comes really, really close to this line here, the graph's going to come really, really close to it, but not touch it. And then this here, that 0 line, the graph is going to come really, really close but not touch it. We, of course, have names for those, and we know that these are called asymptotes. So you've got a vertical and a horizontal asymptote, and that's outlined in the box. A vertical asymptote and a horizontal asymptote. So in this inverse relationship that we're talking about, there are asymptotes because the work still has to get done, and it gets really, really close to 0 but doesn't touch. And vice versa, it would take an infinite amount of time but not actually get to 0 because the work still gets done, even if you had the slowest worker in the world. Number 7, suggest a rule in words that relates the time required to clean up and the number of hours. Explain your reasoning. Well, the time it took, and we already considered this, the time is found by taking the 18 hours of work that needs to be done, and you divide it by the number of workers. That's the relationship that we're considering at. So it's a division instead of a multiplication. How does that look as an equation? So in this case, time was given to us in hours. We have the 18, and we're dividing it by W. Well, now this starts to look like what we know as rational expressions. Our base one is y equals 1 over x. We know that one. That's our rational expression, our rational function, our rational equation. This one happens to be 18 over x. But you see how this is a real-life situation of the rational expression. The only catch is we're only seeing part of the graph. We see that here's that graph. We know technically there's another part of that graph over here. But in this case, we're not talking negatives or positives. We're just talking just the positive scenario. So we make a conclusion about how this relationship between cleanup time and the number of workers is inversely proportional. Well, it really goes back to what I've already mentioned. In grade 9, you had stuff like you had proportional relationships. Stuff like y equals 18x. And this was 18 times x. So if you got paid $18 an hour to work and you worked more hours, then your number would increase by x. Well, now we're going to start to look at inversely proportional relationships. So the example we see here is 18 over x, and it's 18 divided by x. So I bring this up as a good way to start, because pretty soon we're going to get we're just going to be worrying about these graphs, and we're going to get into obscure situations. But I want to remind us that this isn't just coming out of the middle of nowhere. It's coming from a real scenario. It's just an inverse proportion. And the thing we're going to do next is really consider this. Look at how graphs look like in one way, but then look at the inverse, or sorry, the division instead of the multiplication, and we'll end up with these rational functions, which is what this whole unit's about.